Hello guys, welcome to the reinforcement learning series, and this video is going to be part 2 of the value iteration method and Q learning. I hope you have watched part 1. If not, then please go and watch it. Link is in the description. So let's begin. Here we have one action which can lead to three different states with different probabilities with probability P1, and the action can end up in state S1 with P2 in state S2 and with P3 in state S3. That is P1 plus P2 plus P3 is equal to 1, of course, and every target has its own reward R1, R2 and R3. To calculate this expected value after issuing action 1, we need to sum all values multiplied with their probabilities. So it is going to be like, say, action 1 with probability R1 plus gamma V1, and for P2 R2 plus gamma V2, and for P3 R3 plus gamma V3. So that is how it is, and we can write it this in more formal way, like V for action this we need to take RSA plus discounted reward value. It is going to be end up in state, and this is small s to big S, and probability from initial action to RSA plus discounted reward. Okay, so by combining the Bellman equation for a deterministic case with a value for stochastic actions, we get the Bellman optimality equation for a general case, that is maximum of and guys, this is small s and this is big S, so I can write it over like this. So wherever it is written over here in S2 like this S, so this is bigger S and this is smaller S. Okay, so don't get confused with that. Alright, so plus gamma Vs, fine, and this is basically maximum of probability action 0 to S and RSA plus discounted reward to factor. Yeah, so the interpretation is still the same. The optimal value of the state is equal to the action, which gives us the maximum possible expected immediate reward plus the discounted long-term reward for the next state. And you may also notice that this definition is recursive. The value of state is defined via the values via the immediately reachable state. This recursion may look like cheating. We define some value pretending that we already know it, and however this is a very powerful and common technique in computer science and even in math in general, and proof by induction is based on the same trick. This Bellman equation is a foundation not only in reinforcement learning but also in much more general dynamic programming, which is widely used method for solving practical optimization problems. And these values not only gives us the best reward that we can get obtain, but they basically give us the optimal policy to obtain that reward. And if our agent knows the value for every state, then it automatically knows how to gather all this reward. So thanks for the Bellman's optimality proof. At every state the agent ends up in, and it needs to select the action with the maximum expected reward, which is a sum of immediate reward and one step discounted long term reward. So that's it. And those values are really useful to know before you get familiar with a practical way to calculate them. The value of action, to make our life slightly easier, we can define different quantities in the addition to the value of state, Vs, as the value of action. Like value of state is the Vs, value of action QSA as the value, and basically this equals the total reward we can get by executing action A in state S, can be defined via Vs. Being a much less fundamental entity than Vs, this whole quantity gives a name to the whole family of methods called Q learning because it is more convenient. In these methods, our primary objective is to get values of Q for every pair of state and action. So we can write it in this specific way: QSA. So it is going to be very similar to what we have. So this is the S dash, that means that's a recursive value. Okay. Oops. I should write it again. Yeah. Fine. And this is basically S dash. Okay, let's write it in more clear fashion. S dash to big S, and this action to the next state it end up in, and okay, so Q for this state S and action A equals the expected immediate reward and discounted long-term reward of the destination state. We can also define Vs via QSA. So as you can simply see this, like this is similar to this. So we can replace this part with this. So let's write it. Okay, let's go into new page. Okay, fine. So basically we can write it in this specific way, like Vs is actually maximum of QSA. This means that the value of some states equals to the value of the maximum action we can execute from this state. Finally, we can express QSA recursively with the simplest formula, like QSA and the index on the immediate reward SA depends on the environment details. If immediate reward is given to us after executing a particular action A from state S, index SA is used and the formula is exactly as shown above. But if reward is provided for reaching some state S dash via action A dash, the reward will have index S dash comma A dash and will need to be moved into the max operator. That difference is not very significant from mathematical point of view, but it could be important during the implementation of methods. So the first situation is more common, so we will stick to the preceding formula. To give you a concrete example, let us consider an environment that is similar to frozen lake but has a much more simpler structure. We have one initial state S0 surrounded by 4 target state S1, S2, S3, S4 with different rewards. So I'm going to represent it like this specific way. Okay, S0, S1, S2, S3 and S4. Okay, so S dot is 0 is initial state, and S1, S2, S3, S4 are the final state. So every action is probabilistic in the same way as frozen lake, with a 33% chance that our action will be executed without modifications, but with a 33% chance that we will slip to the left relatively of our target cell, and a 33% chance that we will slip to the right. For simplicity, we use discounting factor gamma is equal to 1. So basically, let's calculate the values of the actions to begin with. Terminal state from S1, S2, S3, S4 have no outbound connection, so Q for those states is 0 for all actions. Due to this, the value of terminal states are equal to their immediate reward. Once we get there, our episode ends without any subsequent states. So we have V2 2, V3 3 and V4 4. Okay, the values of action for state 0 are a bit more complicated. Let's start with up action. It's according to definition is equal to the expected sum of immediate reward plus long-term value for subsequent steps. We have no subsequent steps for any possible transition for the up action, so we can write it as up action V3 and V4. So we have 0 into 1 plus 0.33 into 2 plus not this. Oops, did a mistake over here. As V4, that's it, because from up action it only contains to S2, S1, S4. No chance of like ending up in S3 because it's totally down. Okay, so the calculation is going to be very simple. 0.33 into 2 plus 0.33 into 4, and it is going to be 2.31. okay, repeating this for the rest of the S0 action results in the following. So repeating this for the rest of the S0, the action results are going to be, let's go on a new page. Okay, Q for left, it is going to be okay, perfect, it is going to be 1.98, and for right 0.3 into 4 and 0.3 into V1 and 0.33 into V3, and it is going to be 2.64, and for down we have 0.33 into V3 plus 0.33 into V2 plus 0.33 into V4, and it is going to be 2.97. So Q values are much more convenient in practice. As for the agent, it's much more simpler to make decision about action based on Q than on V. In case of Q, to choose the action based on the state, the agent just needs to calculate Q for all available action using the current state and choose the action with the largest value of Q. To do the same using the values of the state, the agent needs to know not only the values but also probabilities for transition. So in practice, we rarely know them in advance, so the agent needs to estimate transition probabilities for every action and state pair. And this is a very good formula, specifically the Q learning. And okay, so we're going to take a scenario like where we have S1 and we go here with the reward is equal to 1 and S2 and then back again with the reward is equal to 2. So we start from state S1 and the only action we can take lets us to state S2. We get the reward 1 and the only transition from S2 is an action which brings us back to S1. So the life of our agent is an infinite sequence of states S1, S2, S1, S2 and so on. And to deal with this infinite loop, we can use a discount factor, say gamma is equal to 9. Now the question is, what are the values for both the states? The answer is not very complicated. In fact, every transition from S1 to S2 gives us a reward of 1 and every back transition gives us 2. So our sequence of rewards will be 1 2 1 2 1 2 and so on. As there is only one action available in every state, our agent has no choice, so we can omit the max operation and formulas, and the value for every state will be equal to infinite sum. So we can write it like in this specific way. So 1 plus gamma 2 plus 1 plus gamma 2 plus and so on, and 2 initial to infinity, and it is going to be 2i plus 2y plus 1. And for state 2, same and a little different. So on. Infinity 2i plus 1 gamma 2y plus 1. Okay, so we can't calculate the exact values for our states, but with gamma zero point 0.9 the contribution of every transition quickly decreases over time. For example, 10 steps it is going to be 0.910 or to 0.349, but after 100 epochs it becomes just like 0.0000266, something like that. And due to this we can stop after 50 iteration and it still get quite a precise estimation. And this example can be used to get the gist of a more general procedure called the value iteration method, and this value allows us to numerically calculate the values of the state and values of action of Markov decision processes with known transition probabilities and rewards. And basically the algorithm, the steps, we're going to write it like, first I'm going to clear the page. Okay, fine. So this is going to be very simple steps. So for simple value iteration method, okay, so the first step is going to be initialize the value of all states, and just basically to some initial value that is definitely usually 0. Okay, and the second is for every state in the Markov decision process, writing it as MDP, will perform the Bellman update, and it is going to be Vs is equal to maximum okay, and we're going to repeat to the second step for some large number of steps until the chains become too small. Okay, so this is the third step, like to repeat to step 2 for some large number of steps until the changes becomes too small. All right, fine. And in case of Q learning, it is going to be similar. That's for Q learning. So the first step is initialize QSA to 0, and the second step for every state S and action A, we're going to perform the update, that is for QSA it is going to be RSA plus gamma max of QSA dash, that is going to be next state and next action, and same repeat until step 2. So that was all the theory. In practice, this method has several obvious limitations. And first of all, our state space should be discrete and small enough to perform multiple iterations over all state. And this is not an issue for Frozen Lake 4 into 4, and even for Frozen Lake 8 into 8. And but for card pool, it's not totally clear what to do. Our observation for card pool is 4 float values, which represent some physical characteristics of the system. Even a small difference in those values could have an influence on the state's value. A potential solution for that could be discretization of our observation values. For example, we can split the observation space of card pole into bins and treat every bin as an individual discrete state in space. However, this will create lots of practical problems, such as how large bin intervals should be and how much data from the environment we will need to estimate our values. And the second practical problem arises from the fact that we rarely know the transition probability for the actions and reward metrics. So remember the interface provided by Jim to agent, and we observe the state, decide an action, and only then we do what we get the next observation and reward for the transition. And we don't know what the probabilities of getting into state S1 from state S0 by issuing action A0. What we do not have is just the history from agents interaction with the environment. However, in Bellman's update we need both a reward for every transition and the probability of this transition. So the obvious answer to this issue is to use our agent experience as an estimation for both the unknowns. Rewards could be used as they are. We just need to remember what reward we got on the transition from state S0 to S1 using action A, but to estimate probabilities, we need maintain counters for every tuple S0, S1 and A and normalize them, and that's it. So, okay, and next video we'll look at how the value iteration method will work for Frozen Lake, the full code explanation and see it in working. And thank you for watching the video, and please subscribe the channel.